Okay, now this is the first lecture about the quantum mechanics. And today we'll begin to study the fundamental postulates in quantum mechanics and Hilbert space. I have told you before that we have two parts in our course. The first part is a Hilbert space related. Topics. Because we are advanced quantum mechanics, we have two parts of the advanced. What is advanced? The first thing is that we have a new mathematics tool that is Hilbert space. And the second part is the group theory. Related. So, in the Hilbert space related things, we have the state vector and operators. So we have the theory for the state vector and operators. And so, based on this, we have the concept of the quantum measurement. And also, based on this, we have the dynamics and have some very special contents of the quantum mechanics, that is the identical particle. So actually, in the Hilbert space related things, we have 1, 2, 3, 4, and 5 fundamental postulates in quantum mechanics. So all of the quantum mechanics are based on the 5 fundamental postulates. The postulates are state vector postulate, or the state vector postulate, and operator postulate, the measurement postulate, dynamics postulate, and the postulates of identical particles. The last postulate is also termed as the symmetrization postulate. And here, in the fundamental postulates in quantum mechanics and Hilbert space, we will study the first 3 postulates first. That is the chapter 1 of all of the lectures in this course. And after that, we'll study the dynamics. That is a time-dependent, time evolution of the state or the operators of the systems. And the last postulates are very specialized. That is related to many particle systems, for the identical particle, for the bosons and for the fermions, for the second quantizations, for the field theory, and so on. So very eventually we'll mention something about the identical particles. That is not the important point of this course. So we'll focus on the first 3 postulates and the dynamics of the systems in this course. We'll mention a little bit about the identical particles later, very little. And so this is the first part of the whole course, that is Hilbert space related. And another thing is group theory related. That is the problems of the symmetry and conservation in quantum mechanics. The symmetry and conservation. Symmetry is a very important concept in all of the physics, especially in quantum mechanics. Actually, in classical mechanics, we have already mentioned many things about the symmetry or symmetry transformations. If you have some spatial translations, you got some invariance, that means you have the conservation of the momentum, right? If you have some rotation invariance, that is related to the conservation of the angular momentum. If you have the translation in time and got invariance, that is the conservation of the energy, right? We have mentioned that in classical mechanics, but not more. But in quantum mechanics, we have too many conservations, too many symmetries, not only in the time and space translation. We also have the space rotations. We have the reflection in space. The reflection in space also means the spatial inversion, and it is also called the parity transformations. And parity is a very new term. It is the space or the spatial inversion or the reflection. You have the x transformed to the minus x, that is the spatial reflection or spatial inversion or the space reflection or inversion. And normally we call it in a very simple term that is called the parity. We have the parity transformation. And parity transformation is very important in quantum mechanics. And also we have the conservation in parity. But we do not have the parity conservation in classical mechanics. So parity conservation is a very, very special thing in quantum mechanics. Okay. And also we have the symmetry transformations related to the time inversion or the time reflection. That is called the time reversal. In time reversal, we don't have any conservation laws. We don't have any time reversal related conservations, but we have many other important physical phenomena that is related to the time reversal. For example, we have the Cramer's degeneracy due to the time reversal. That is called the Cramer's degeneracy. And this is related to the time reversal. Time reversal. Time reversal means the time transferred to the minus t, the t changed to minus t. And then you got these kinds of degeneracy that is called the Cramer's degeneracy. That happens for the systems, for example, in the atoms with the angular spin to be a half integer, and then you got the time reversal, and you have the Cramer's degeneracy. But if you do not have your system, your spin of your system is integer, you don't have this. If your spin of your system is half integer, you have the Cramer's degeneracy due to the time reversal symmetry. Okay, so for this one symmetry, one conservation, or one symmetry, one some physical or quantum mechanical phenomena, you should have you should study the mathematical theory of the symmetry related things, that is group theory. And we have two kinds of group in our quantum mechanics. One is discrete symmetry. So we have the discrete group. And another thing is the continuous. So our space reflection is discrete. Time reversal, discrete. And also we have several other discrete group. We are more interested in the continuous group, and it is called the Lie group. The Lie group is a continuous group. We have the space translation, we have the time translation, we have the space rotation. They are all continuous. So they are Lie group. So we'll study this And this is the advanced topic, and this is the basic topic. We have two parts in the whole course. Hilbert space, a little bit more basic, right? And group theory is a little bit more advanced. But for most of the students in this classroom taking this course, you should be very interested in the advanced topics in quantum mechanics, because most of the guys here are related to the atomic physics. Atomic physics means that you have many relations with angular momentum. And angular momentum is tightly connected with the Lie group. What kind of Lie group? You have SO3 and SO4 group. And also, you have the SU2 group. So they are all Lie groups. And they are all related to the angular momentum. That's very important. So you should be very careful, very intensively to study the topics of advanced quantum mechanics, especially for the angular momentum theory and the related group theory and Lie group and Lie algebra theories. Okay? So that's a very, very brief introduction about the whole contents of the advanced quantum mechanics course. Okay. Another thing, let's summarize what we have learned in the classical physics, in classical mechanics, classical electrodynamics, and the statistical mechanics and so on, in some mathematics that we have learned before, or the mathematics and the physics background that we have before the occurrence of the quantum mechanics. So we have the toolbox, right? We have the toolbox offered by classical physics and mathematics. Classical physics means that we have the classical mechanics, we have the classical electrodynamics, statistical mechanics, and so on. And mathematics, how many mathematics do you learn or before the quantum mechanics? We have already had almost all of the mathematics that is necessary for the quantum mechanics, right? You can think about it, how many mathematics you have learned. There are very few mathematics that is only useful in quantum mechanics. Most of the mathematics quantum mechanics need have been available before quantum mechanics, right? How many? You have the calculus. You have the linear algebra. Or maybe you have some statistics. You have the ordinary differential equation and the partial differential equations, and special functions or something. So you have already had almost all of the mathematics that is necessary for you to study the quantum mechanics. There are not so many new mathematics, not so many. I think that only one mathematics that is needed in quantum mechanics is the delta function, probably. We have already had the calculus and also have the functional analysis. For example, we have the Hilbert space. Actually, before quantum mechanics, we have already had the Hilbert space. And also, we have already had the group theory. There were several very genius guys, very talented guys in the group theory. They are very young and then died. For example, the Garwan, and also the Sophus Lee, And also the Abel, they are all very famous in group theory. And they are very young, and they die. Galois, and also the Abel, they are before 20 years old or before 30 years old, they died. But they have left so many very valuable things in mathematics that we have the group theory. And Sophus Lee is also not so old. I think that he's only about 50 years old or something. And then I have told you some story about the Sophus Lee. Lee is very important because we have the Lie group and the Lie algebra. He has been sent to prison in the Russian Empire. He is from the Norwegian. He's a Norwegian guy. And all the things have been available before the quantum mechanics. And so we have already had so many mathematics and we have so many physics, so everything is ready. Especially, from the classical mechanics, we have already had several very important things. The first thing is that we have already had the Hamiltonian. The Hamiltonian is very important because in non-relativistic quantum mechanics, the key, the core, is the Hamiltonian, right? We have already had the many canonical things. We have the canonical coordinate, the position, and the momentum. Yeah? So in quantum mechanics, keep in mind that all of the position and momentum should be canonical, and not the kinetic position, kinetic momentum. They should be the canonical position and canonical momentum. Remember that. That's a very important thing. In quantum mechanics, all of the positions, all of the momentum should be the canonical coordinates. Okay, that's a very important key. And also we have the canonical commutator. Okay, we have already had the xi, pj, Poisson bracket. That is called the classical canonical commutator, right? Then this commutator equals to third ij. Okay, and also you can have too many other commutators. You can have the commutator before the between the xi, xj, pi, pj, li, lj, and so on. You can calculate yourself by definition and by the properties of the commutator, the Poisson bracket. Remember, we have already learned and studied this many times. We have emphasized the classical canonical commutator in several of our lectures, right? Remember? That's very important. So this relation comes from classical mechanics. And from this, we can generalize to the quantum mechanics. In quantum mechanics, we'll have the QCC. And because this is the PCC or the CCC, right? PCC means Poissoning, canonical commutator. And CCC is classical canonical commutator. That's the same. And QCC means the quantum canonical commutator. So now you're from P, you generalize to Q. Right? So that's a generalization from P to Q. Okay, that's very interesting. And from this, we know that the A and B, the Poisson bracket, will be generalized to this. A, B, one over h bar. And another change is here. You change the A and B to the A hat and B hat. That means this is the C number function. What is the C number function? The classical function, commutable function, commuting function, whatever. That means the A times B equals to B times A. But when you have the A hat and B hat, normally AB is not equal to BA. Okay, so generally speaking, AB is not commutable. Is not commutable in quantum mechanics. So this is called the C number. The C here, you can think of the C as the classical, of course, and commuting or commutable. Okay? And here is called the Q number. Q number could be an operator or a vector in Hilbert space. We will mention later what is the operator and what is the state vector. So normally, AB is not equal to BA. But for the C number, we have the AB is equal to BA. But AB is equal to BA doesn't mean that partial A, partial Q, partial B, partial P minus partial A, partial P, partial A, partial Q is equal to 0. It doesn't mean that. Right? So we have the Poissonian bracket here. That means the partial A, partial Q, partial B, partial P minus partial A, partial P, partial B, partial Q. Right? So, and the classical and quantum thing, you have a difference in the factor here that is a 1 over I h bar. And all of the calculation results for the Poissonian bracket that in the exercises, in the homework you will accomplish, you can do a lot of calculations before quantum mechanics. And all of that can be just shifted to the quantum mechanics by just inserting such a factor, 1 over I h bar. You can verify that. So after you finish all of the classical mechanics homework, when you encounter the similar homework in quantum mechanics, you just do not need to calculate. You just need to insert such a factor. That's enough. So that's why I told you that at the very beginning, you could be a little bit tough, a very hard job, it's a lot of work, no problems. After that, you have learned all of the quantum mechanics, almost. Maybe 70% or 80% or something. Okay, understand what I mean? Okay. And also we have from the commutator, we have the canonical equation of motion. Right? Because the equation is very simple. It is just the df over dt is equal to partial f partial t plus f h pb. And that is the generalized form of the canonical equation of motion in Hamiltonian mechanics. And this equation can be generalized to the quantum mechanics also. We have the two similar equations in quantum mechanics. One is called the Heisenberg equation. Another thing is that Ehrenfest equation or the theorem. Okay, I'm not sure if I have enough space to, well, okay. The Heisenberg equation is like the df over dt is equal to the partial f partial t plus 1 over I h bar. And then you have the f h. And that is the quantum commutator. So this is the Heisenberg equation in the Heisenberg picture. We will study the three pictures in quantum mechanics in this course. We have the Schrödinger picture, and then you have the Schrödinger equation. And we have the Heisenberg picture, we have the Heisenberg equation. And also we have the Dirac picture. And the Dirac picture is called the interaction picture. We have both the Schrödinger equation and Heisenberg equation, but there are some small changes. And also we have the Ehrenfest theorem. That is the evolution of the average or the expectation value of something. For example, we have the f, that is observable, and that is the expectation value of that. And the over dt, the average or the mean value of f is equal to the average or the expectation value of the partial f partial t plus a h bar, the commutator between the f and h, and then take the expectation value. So that is the Ehrenfest theorem. So you can compare the Heisenberg equation and the Ehrenfest theorem with the canonical equation of motion in Hamiltonian mechanics. You can find that it's very similar. And the only difference is that you have a factor here. That is, but we have already told you that from classical to quantum, you have the 1 over h bar factor. And when you just change in this way, and every equation you can derive very easily, right? So actually, the people have been very, very much available, for everything is ready for the quantum mechanics. And one important point is that for the canonical thing, we have the canonical transformation. The canonical transformation means that if you change from QP to the capital Q, capital P, and correspondingly, if you change from the old Hamiltonian to the new Hamiltonian, and all of the coordinates and Hamiltonian has been changed, but there are very important thing that is kept invariant, unchanged. What's that? This. You'll find the Poissonian bracket, the value of that will be kept invariant. So, you have the Q, I, P, J, PB is equal to this. When you change to the capital QI, capital PJ, that keep the same. So that means once you choose the canonical coordinate, all the relations will be kept invariant. So this is the right choice for the canonical coordinates. So the canonical coordinate is called the right coordinates. Right coordinates, right commutator, right equation, and right transformations. Canonical means right. Right? But if you do not choose the canonical coordinate from the very beginning, if you choose the canonicalization or kinetic momentum, all the properties of the unchanged things of the commutator and equation and so on cannot be kept. So it's very important for you to choose the canonical coordinates first. And then the commutator should be canonical. Transformation, canonical. Everything should be canonical. And then you got the, from one of the choice, you got some right results. And then even you change, if even you have the transformations, canonical transformations, nothing will be changed. Got it? Okay. So that's why the canonical thing is so important. Canonical. So sometimes we call the Hamiltonian mechanics as the canonical mechanics. Because it is based on the Hamiltonian, based on the canonical coordinates, and so based on the phase space, and based on the right coordinates, commutator, equation, transformations. And all of the non-relativistic quantum mechanics is based on the canonical things. So the very early quantization is called the canonical quantization. Canonical quantization. That is the first quantization procedure. And for a very long time, maybe 20 years or something, That is the only quantization procedure in quantum mechanics. At the very beginning, we have only the canonical quantization. We don't have the other procedure of quantizations in quantum mechanics. But 20 years later, maybe, for the Richard Feynman, he introduced the Lagrangian-based quantum mechanics. He introduced the path integral, and after the path integral and propagator, the people have another new version of quantum mechanics. That is Lagrangian-based quantum mechanics. But for a long time, the people only have the Hamiltonian-based or the canonical quantization-based quantum mechanics. Okay? So for this course, the canonical quantization is the major. We do not spend much time about the Lagrangian or the path integral or propagator or something based quantum mechanics. We'll focus on the canonical quantization and this kind of non-relativistic quantum mechanics. Okay, so, and for the canonical quantization, that there are only two things that you should do. The first thing is that make every physical quantity or the observable from C number to an operator, to a Q number. So in classical, it is a C number, right? It is a very common function. It is not an operator. But in quantum mechanics, it should be changed to an operator. That is one thing. Another thing is that you will have the canonical commutator relation. And for us, the very fundamental canonical commutation relation is this. In quantum mechanics, the very basic or the fundamental commutation relations is this. Xi, Pj, X and P has been changed to the Q number is equal to IH bar dirt Ij. So you find that the only difference between this and this is only you have a factor that is IH bar. Then this is a Poissonian bracket, and this is the quantum commutator bracket. Okay? So that's very simple. That's very simple. Okay. And also, I think that the toolbox of the classical physics and mathematics have offered us to have the new mechanics, the quantum mechanics, is that we have a very important concept. That concept is called a state. Actually, in the phase space in Hamiltonian mechanics, we have the phase space, right? We have a phase space that is the Q and P. That is the phase space. And each point, that is called the phase point. We have studied the Lovey theorem. Do you remember that? We have the concept of the phase space and phase point in this space. And each point in phase space is called a state. So that is a very early and very original definitions of the state. Before that, in mechanics, we don't have the concept of the state. So state is a very important concept in classical mechanics. And from classical mechanics to the quantum mechanics, because we have already had the concept of the state, so we can have the state. So we can have the state postulate. That is the first postulate in quantum mechanics. Remember? Okay. So we have already had the concept of the state. We have already had the mathematical procedures of Poissonian bracket, and we have Hamiltonian canonical things and so many things in classical mechanics. So we have sufficient tools already before the new mechanics come, before the quantum mechanics, right? Everything has been ready. So now, 1, 2, 3, you can go. Right, okay? So that's very brief and global stories about of the classical mechanics and mathematics and so on. Everything has been ready for the creation of the new mechanics that is called the quantum mechanics. So, and one more thing that I want to mention here is that we have mentioned two important things. One is Hilbert space, right? This is H and this is G, the group theory. Both things come from the same place. And that place is called the Göttingen University. H plus G comes from the same place. The grand part in here, in the Department of Mathematics, is called Minkowski and Hilbert and some very famous mathematicians. They have created some culture in mathematics in Göttingen. And you know, of course, the Hilbert space comes from Hilbert. And Hilbert, at the period of the quantum mechanics, David Hilbert has been an old and very famous, very well-known, very big professor already. Another thing is group theory. I have mentioned that we have already had the group theories by Galois, a French guy, and also we have the Albert, that is also a guy from the North Europe, and also we have Sophus Lee, that is also from the North Europe, from Norwegian. We have already had that group theory, but we have not yet applied all these group theories in physics. At least not much in physics. But there are some very young guys during 1926 or 1927 or something, just around that time, two young guys from Hungary, they moved to Göttingen and studied and worked with Hilbert and some old, very famous guys in mathematics. And also at that time, a very famous young professor whose name is Max Born is also working at the Göttingen. So the application of the group theory is Wigner. And this guy is a Hungarian guy. He's from Hungary. And we have another guy who is maybe 1 year younger than the Eugene Wigner, but he was from the same high school as this guy, to Hungary, Eugene Wigner, and also von Neumann. And von Neumann studied with Hilbert. And around 1930s, this von Neumann proposed the postulates of quantum mechanics. That is called the axioms of or the fundamental postulates of quantum mechanics. A topic, fundamental postulates. We have 5 postulates. But the von Neumann and Dirac proposed 1, 2, 3. The first 3 postulates at the very beginning. The state postulate, the operate postulate, and also the measurement postulate. That was proposed by Dirac in 1930, and in 1932 proposed very rigorously by von Neumann. So among 5 very fundamental postulates, this guy, von Neumann, and Dirac proposed the 3 of them. So just around 1930s, the postulates or the axiomatization systems of all of the quantum mechanics has been constructed. And that is what we should study and learn from today on. That is the fundamental postulates. So the first postulate one, state postulate. And postulate 2 is the operator postulate. And postulate 3, that is called the measurement postulate. And postulate 4 is called the dynamics. And postulate 5, identical particle postulate. And it is also called the symmetrization postulate. Okay, let's focus on some of the key words. One is the state postulate. The second one, the operator. And the third one is the measurement. And measurement, okay, so this is so important that we should emphasize many times. And this is dynamics and identical particle. So we have 5 key words: state, operator, measurement, dynamics, and identical particles. 1, 2, 3, 4, 5. And sometimes the people like to combine the first 2 postulates into one postulate. That is got the state or the vector operator postulate. Okay. So actually, the first postulate means that all of the microscopic system is described by a state vector. That is a state vector in Hilbert space. And this is Hilbert space, like this. And the operator means that all of the physical quantity is described by a linear and Hermitian operator. And this linear Hermitian operator can operate on the state vector in Hilbert space. So the key word is that linear and Hermitian. And the measurement is very complicated. So I think that I have not enough time to describe in detail about the measurement postulate. This postulate has many, debate. But the major stream in quantum mechanics today, the people believe that the Copenhagen's interpretation of the measurement postulate is acceptable. So the measurement postulate, though it is complicated, but we just accept the interpretation of this. And the measurement postulate will be discussed later in detail. And the dynamics postulate is that it is an equation. And this equation is called the Schrödinger equation. And this equation is in the picture. This picture is called the Schrödinger picture. In the Schrödinger picture, you have this equation. And equivalently, you have another version of this postulate that is in the Heisenberg picture. And in Heisenberg picture, you have the Heisenberg equation. And we are not will not spend too much time to discuss the Heisenberg equation because most of the people prefer to adopt the Schrödinger picture and Schrödinger equation. And the last postulate is the identical particle postulate. The symmetrization postulate means that if you change the positions of two identical particles in a system, if you have n particle systems, if you change the position of any arbitrary two particle, that is particle I and particle J, and the system will be, the state will be kept invariant. But it has two possibilities for these symmetric transformations. That is, for bosons, you have the symmetry, but for the fermion, you have the anti-symmetry of that. Okay, so that is for all of the 5 postulates. That is the fundamental postulates in quantum mechanics. That is the very starting point of all of the quantum mechanics. But remember that all of the 5 postulates are only valid. Remember that. It should be valid for what? For non-relativistic quantum mechanics. In our lecture notes, I have listed several versions of the fundamental postulates because I have listed the version 1, version 2, and version 3. For the version 1, that is only valid for the pure state. We have a very, very strong confinement. We have very strong restrictions. Not only the non-relativistic, that is of course a very, very strong restrictions. All of these things should be based on relativistic case. For the relativistic case, know these postulates. Okay? And for the first version, we prefer the first, and the second version is the pure state. And the third version in the lecture notes, that is for both the mixed and the pure state. Both are okay. Okay? So for the pure state, the state can be described by a state vector, but for the mixed state, no, you cannot use that. You must use this. So the first postulate should be modified like this. The state vector cannot be used to depict the state. For a mixed state, we must use the density operator to describe a system. We cannot use this. This is not valid. And also, all of the postulates are based on another restriction that is called the closed systems. We have the non-relativistic and it should be the closed system. For an open system, it doesn't hold. So these two restrictions are very strong. We should keep in mind non-relativistic and closed systems. All of the postulates should be based on that. Okay, we can take a break. Okay, welcome to the Hilbert space. the first thing that I want to mention is that the concept of the Hilbert space. The Hilbert space is different for the mathematics and physics. In mathematics, Hilbert space is very similar to the Euclidean space. In Euclidean space, you can have the n-dimensional, and n could be infinite, but it must be integer. But in physics, the Hilbert space had been generalized to infinite and also to uncountable infinite. For the mathematics and for the physics. It could be like this. The dimension n-dimensional. It can be finite, and also it can be infinite. But the infinite is countable. So that means you have the 1 dimension, 2 dimension, 3, 4, 5, and so on. That's okay. And then up to the infinite. That's okay. That's countable. But for the physics, and it also denoted like this, the n dimension, no, could be finite or the infinite, but it could be countable and uncountable. So for the mathematics, we have the orthogonal and normalization completeness relations like this. That is the psi I, psi j is equal to the delta ij, and psi I is equal to the identity. So this is the orthonormal relation. And this is the identity, the resolution of the identity, or the completeness condition. But for the physics, we have this, and also we have another generalization, that is the psi prime. Oh no, let's use another thing. We have the a prime is equal to delta a minus a prime, and this is also called the orthonormal relations for the continuous versions of the Hilbert space. So in physics, we have this. We have the delta function normalization. But in the mathematics, we only have the chronic delta. We do not have the delta function. And for the completeness, or the identity, the resolution of identity, we have this. So for the physics, we have both this and this case. For the physics, we have both. So that is a generalization of the Hilbert space in mathematics to physics, like this. Okay? Got it?
Yes.
So rigorously speaking, the Hilbert space for the physicist is not the Hilbert space in a very mathematically rigorous way. But for the physicist, that is the generalized Hilbert space is just the Hilbert space. It is a complex space. And for the physicist, it is also a complex space because the numbers here belong to the complex number. but for the Euclidean, it is a real number. That is an important point that I want to mention here. Okay. Another thing is that a Hilbert space is a linear. It's a linear space. So linear means it is a vector space. In physics, vector is translated into Chinese like this. But the same item is translated into Chinese like this. Right? I think that in grade 1, when you are undergrad student, you have learned the linear algebra, right? Okay, so Hilbert space is a linear space or is a vector space. And also, it is not only a linear space, but it is also an inner product space. It's an inner product space. So for the Hilbert space, we have the definitions for the vectors in this space. And this vector in Hilbert space is called, for the physicists, we call the vector in Hilbert space as state vector. And for this vector, we use this notation. And this thing is called the ket. This is called the ket. And each ket has a door vector. This is the door vector. So this is a vector. It is called the ket. And this is the door of this ket. This is called door. In Chinese, it is translated like this. And what does it mean? It means this. And this guy is called the adjoint. For the mathematics, it is called adjoint. And for physics, it is called the Hermitian conjugate. The two names are equivalent, are the same, especially for the accountable infinitesimal dimensions. They are completely adjoint, the equivalent. Okay, but this operation is very important for the quantum mechanics because you always face the conjugate. This is called the Hermitian conjugate. In mathematics, it is called the adjoint. And for this, we call it as a brawl. And the brawl and ket together, you have the bracket. If you connect it by C, it is called the bracket. So, brawl, ket, connected, bracket. Okay. This is my understanding of the name of the brawl and ket. And for this, we can also have the and if we have the adjoint and then adjoint, it keeps invariant. Okay, so these are very important rule for the operation. Okay, so and what does it mean for the inner product space? Inner product space means that you have the door stay vector and this vector, that is bro and cat, and then you have the inner. That is, inner product means this guy and this guy is something of, it's a number, and this number belongs to the complex number. So we have the following several operations for the state vector. One is the vector addition. If for any psi 1 and psi 2 belong to this Hilbert space, and then psi 1 plus psi 2 belong to the Hilbert space. So that is the vector addition. And also we have the scalar multiplication. For arbitrary psi belong to the Hilbert space, and C is a C number. It's a C number. It's a scalar. It is belong to the complex number, and then you got the C psi also belong to the Hilbert space. So that is the scalar multiplication. And also we have the inner product, of course. Inner product means that you have two states, psi 1 and psi 2. And this is the inner product of these two vectors. It is equal to this. And it is some complex number. So if you have the inner product of the two states, you got the number. If you have a scalar multiplication of one vector and another C number, you get the vector. If you have the two vectors, you have addition, you got another vector. Got it? So that's the definitions of some very basic operation rules for that. And I think that you have the operations of this, and this is also one of the operations adjoint. Okay, and you can, when you go back home, you can study the details of the vectors in Hilbert space in details, and I will not spend much time over that. Well, I want to mention one of the properties of some operations of the vectors. That is, for any psi 1, psi 2, the inner product is equal to C. It should belong to the complex number. It is a complex number. So from this, you can derive for arbitrary state vector psi psi. And if it equals to this R, right? Because we have the rule for the psi 1, psi 2. The inner product is equal to the psi 2, psi 1. And they are the complex conjugate. If you change the position of the two vectors, you've got this complex conjugate. Of that. Okay. So from this, you can find that the R psi psi equal to the psi psi star. So that means the R star is equal to R. So what does it mean? That means the R belongs to real number. And also, we can derive a more important result. That is, the psi psi is bigger, is greater or equal to 0, provided that if you have the equality if and only if psi is equal to 0. If it is a 0 vector. Okay? So this is a sufficient and necessary condition for the vectors in Hilbert space. Sufficient and necessary condition for that. Provided that you have the psi is equal to the 0 vector, you got the distance or the norm. And this, actually this is equal to another thing that is called the norm of the psi and square. What's the meaning of the norm? Norm means the distance between the two vectors. In geometry, you got the distance, the concept of the distance, and that is a very special case for the norm. Okay? So I think I have told you most of the important properties of that in the Hilbert space. And now we can go to the operator. So next is the operators. Because we have mentioned that the state is described by a vector in Hilbert space. So we have studied the state. The state is a vector. Another thing is the physical quantity. The physical quantity is described by a linear and Hermitian operator. And that linear Hermitian operator is also called the observable. The operator in Hilbert space. But operator, of course, it is a much bigger set than the observable, because we have many kinds of operators, and in quantum mechanics, the most important thing, the most important operator is of course the observable. In Chinese, this thing is called this. What is observable? Observable is a linearly and Hermitian. It's a linear Hermitian operator. So this operator should be linear and also should be Hermitian. So two key points for the operators. And for this, the physical quantity is the linearly Hermitian operator, and this operator is called the observable. I think that I have given you a very clear explanation of what is physical quantity and what is linear Hermitian operator and what is observable. Okay? You got my point? Yes, and that is the second postulate. That is the postulate, the fundamental postulate 2 in quantum mechanics. And also we have another thing that is also very important in operators in Hilbert space. That is the unitary. Transformation. And this transformation is a symmetry transformation. And we have two kinds of operators which can represent the symmetry transformations. One, we have the linearly and unitary transformation. Two key points. It's a linearly operator. It's a linear operator. It's a unitary operator. And also we have another thing that is anti-linear and anti-unitary transformation. So, in quantum mechanics, the operators play the role in these two aspects. One is observable. Observable is connected with the measurement. The observable is something that can be observed. That means it can be measured. So if you have this linear Hermitian operator, that means you have this operator and his Hermitian conjugate is equal to itself, or the adjoint of the operator is equal to itself. So this is the definition and also the property of the linear Hermitian operator. And for transformation operator is more complicated. For the linear unitary transformation, you have U dagger is equal to the inverse of U. And equivalently, it means that the U dagger U is equal to U dagger is equal to identity. So this is the definition and also the property of the linear unitary transformation or linear unitary operator. And that is another very important transformation operator, because we have only two functions for the operators. One is for the observable. It's observable. Another thing is transformation, the symmetry transformations. And most of the symmetry transformation is linear unitary transformation, except one thing. There is only one exception. That is not the linearly unitary transformation. The only one exception is this. We also use this. Actually, but we have, if you have the psi prime is equal to this, you got, for the antilinear anti-unitary transformations, you got the you got what? You got the psi prime, phi prime. The absolute value of this is equal to that psi phi. So this condition is not so restricted. But for this case, is that psi prime is equal to U psi, and phi prime is equal to U phi. And you got that the psi prime, phi prime is equal to psi. So for this, you can find that this, from this relation and this relations, you can derive that very directly. From this relation, you can derive this. But you cannot derive this, because this condition and this condition are different. The difference is here. You have the absolute value here for the anti-unitary case, but for the unitary case, you don't have the absolute value. Okay? We'll study this later in details, but today I just give you a very brief introduction. That's a very preliminary introduction of the linear unitary and anti-linear unitary transformations. So all of the operators in quantum mechanics, only two kinds. One is observable. Observable, what is observable? You have the Hermitiani, you have the position, you have the momentum, you have the angular momentum, you have the parity, and you have some physical quantities that you like to measure, and all the things are the observable, because you can measure that. You can measure and you can observe the observable. So that thing is called the observable. If that thing cannot be observable. It is not observable. Okay, so observable is a noun and also an adjective also in English words. So observable thing is something that can be observable. Okay, you got my point? Okay, another thing is not observable. That's transformation. So altogether in quantum mechanics, there are only two kinds of operators. One is observable, another thing is the transformation. For the observable, it should be Hermitian operator. But for the transformation, it must be unitary or anti-unitary. But sometimes it is also Hermitian. It's very strange that we have something that we have the Trinity. I would like to mention here a very interesting item that is called the Trinity operator. That is Trinity operator. This is my interpretation of that. What does it mean? You have three properties satisfied simultaneously for operators. If you have some operators which has the property of the unitarity and also have the Hermicity and also have the involutarity for the three properties together, and that operator is called the Trinity operator. So this is my invention. I have never seen any items like this. The first thing is, the first property is that Hermitian. It should be Hermitian operator. It should be unitary. And also, it should be involutory. Do you know what's the meaning of this? This item is not so frequently used in Chinese, but it's a very important property in mathematics, especially in a matrix in the linear algebra. It is translated as this, but also it can be translated into Chinese like this. It's very interesting in economics. And what does it mean? Hermitian means that you have the A dagger is equal to itself, right? That's a joint or Hermitian conjugate to be equal to itself. And unitary means that the dagger is equal to its inverse. Okay. And this thing means that the square of this operator is equal to 1 to the identity. So that means the operator is the inverse of itself, right? Because A is equal to identity, right? So that means A is equal to A inverse. So that's why it is called the involutory, because this thing and this thing are the same. And one of the a very important thing that I want to mention here, I want to emphasize here, is that provided that you have any two properties among these three properties, you will have another property. If it is Hermitian and unitary, it must be involutory. Or if it is involutory and unitary, it must be Hermitian. Okay? So all the three properties will be together. So that is 3 in 1 operator. Trinity means 3 in 1. 3 in unity. So that's my invention. I call this properties as the Trinity operator. And how many operators in quantum mechanics which can be called the Trinity operators? I can give you some examples. For example, of the Trinity operator, okay? Oh, I have only such a space. The first example is that Pauli matrix, Pauli operator. Pauli operator is a trinity operator. That is, the sigma square is equal to 1, each component. Okay? Maybe I think it's better for me to write the Pauli operator like this. The Pauli. It is sigma I, the ith component of the Pauli operator, because sigma I square is equal to 1, right? And sigma I dagger is equal to itself. And so sigma I dagger is equal to its inverse. Okay, so this is one thing. And another thing is parity operator. That is called this. P is a parity operator. And P dagger is equal to itself and equal to its inverse. And also P square is equal to identity. Okay, parity operator is related to the space reflection transformation. And parity is very important. It's not the continuous transformation, it is discrete. But this thing is the continuous. This continuous and this is discrete. And both are related to the group theory. And the third thing is that transposition operator, Pij. In an identical particle, if you change the i's and the j's particle, and this stuff is also the trinity operators. Okay? But sometimes many people prefer to use the T because it is a transposition. Transposition is very similar to transpose in a matrix. You have the transpose, right? You have the A transpose, that means you Aij change to Aji. Okay, that's the transpose. So the transposition operator for the identical particles, you just exchange the i's and j's particles positions, and then you got no difference. You got the symmetry or maybe anti-symmetry for that state. But if that is symmetry or anti-symmetry, you got the absolute value of that wave function keeps invariant. So that's why that's a symmetric transformation. So, okay, I think that I have told you many things about the operators. But there are many details about the properties and the calculation regulations for the operators in Hilbert space. You have the operator addition, the operator multiplications. You have the associativity, distributivity, and commutativity of the addition, but you do not have the commutativity for the multiplication for the operators, right? Okay, well, but I think that the most difficult concept of the operator is about the adjoint operator. I think I should spend some more time to mention that. Maybe I can give you some examples to tell you about the eigenvalue and eigenstate problems related to the operators later. Mention about the adjoint operations first. What is adjoint? We have a very simple definition of that. If you have this, the dagger or the adjoint of this is equal to this. This is one of the definitions of the adjoint operations, and it is equivalent to this definition. That is phi a dagger psi. And I want to mention here that that is for arbitrary psi and phi, which belongs to the Hilbert space. For any state vector, you have this relation is equal to psi a and phi. From this definition, you can find that you have the exchange position of this vector and this vector. You just change the position of that. But after this change, you got the complex conjugate. And here, A is a dagger. So because that is valid for arbitrary state vectors of the psi and phi, so this relation holds for the definitions of the adjoint of the operators. Okay? So this is the definition of the adjoint of the operators. And this is also the definition of the adjoint of the operators. And from this you can find some properties of adjoint. And using this definition, you can prove all of the properties here. You can have the A plus B. And together you have addition of A and B, and then you do the adjoint operation, and then you can find that it's equal to the A dagger plus B dagger. And also, if you have some number that is a C number A, and this is the operator A, and you take the adjoint of together, you got the A star. A star means the complex conjugate of this number, and A dagger. Okay? And a very important property of the adjoint is that we have the A dagger and dagger again. You have this. It's unchanged if you dagger twice. And so this is not only valid for the operator, but also for the state vector. That is, I have mentioned that you have the dagger and dagger is equal to psi. And that is also valid for the bra. The dagger of bra and then dagger, you got the bra, right? And of course you have this guy, dagger is equal to this. And this guy, bra, the dagger of bra is equal to the cat. And the final thing that I think is very important is that if you have the A, B, C, something like this, if you have so many operators, and what is the result of the dagger for this operator's multiplication? What is the result of that? I think that I can write this in another way. For example, A1, A2, AN dagger. It is equal to AN dagger, A2 dagger, and A1 dagger. And that is very similar to A1, A2, AN. If you take the inverse, that is equal to the AN inverse, A2 inverse, A1 inverse. I think these relations are very, and we have so many adjoint operations in the future. And also I want to spend some time to mention a thing about the eigenvalue problems. The eigenvalue problem. The eigenvalue problem. The eigenvalue problem. Eigenvalue problem is a problem for the observable. If you have observable like this, you find that if this operator operates on such a state, and the state is the same, and then before that you have a number here, and this number is called the eigenvalue. The eigenvalue of the operators in the Hilbert space is normally a complex number, right? So AN is this. But you can prove that if A is equal to its complex conjugate, Hermitian conjugate, if it's a Hermitian operator, then you can prove that An is a real number. Okay, we have several theorems related to the eigenvalues and eigenstate in the lecture notes, but we have no time to state everything very, very clearly in details, but you should learn it by yourself. When you go home, you can study that from the lecture notes. And this is a case, and this is a discrete case. And each eigenvalue is called the spectrum. And for this case, it is called the discrete spectrum. This is a discrete spectrum. And we also have another possibility that we have this. Right? We have this. And for this case, that is a continuous spectrum. That's a continuous spectrum. If A is the Hermitian, operator, if A is the Hermitian operator, we can have a real eigenvalue. That is one of the results. And also we know that the eigenvector, this is the eigenvector. And for the eigenket, because this is ket, so eigenvector here is called the eigenket. And all of the eigenvectors, or eigenstate, or eigenket, they constitute a orthonormal and complete basis. The basis is orthogonal to each other, and it is normalized, and this is complete. So that is called the orthonormal and complete. And what is the orthogonal? Psi n, psi m, the inner product of this is equal to delta nm. That is the orthogonal and normalized. Okay, because it equals to 1 or 0. 0 means orthogonal. 1 means normalized, right? And psi n is equal to this identity, and that is called the resolution of the identity, and that means the condition for the completeness. So that means you have the orthogonal and normalized basis, and the basis are enough for you to span the whole space in Hilbert space. Okay? Okay, I think that I have completed all of the things that I want to discuss today. And we have also some other more important things that we can learn it next time about the direct sum. Something like this. This is the direct sum. And also we have the tensor product. That is like this. And many people call the tensor product as a direct product. But it's not so good because it is very confused. Because in functional analysis for the mathematics, the direct sum and direct product is the same thing for the functional analysis in mathematics. So it is very confused. So we prefer to use the tensor product if you have two bases to have some tensor product, because the dimensionality for the tensor product is that the dimension of the two state, because that's the product of the two dimensions. And for the direct sum, the dimension is equal to the summation of the two dimensions. So for the functional analysis, the direct sum and the indirect product are the same for the dimensionality, but it's different from the tensor product. So I want to emphasize that we prefer to use the tensor product in quantum mechanics. Otherwise, it is. So, and next time, we'll study this. And also, for all these concepts, we mention something related to the degeneracy in subspace and so on, because for that you can find that you have one eigenvalue corresponds to one eigenstate. That it means that non-degenerate. But sometimes we have only one eigenvalues corresponds to several eigenstates. That means you have some degeneracy. And that's a very important topic in quantum mechanics. So for next time, we'll study that. Okay, that's all for today. Yeah.